Hello students, and welcome to our lesson on parent functions and transformations. This is arguably the most important lesson in terms of preparing you for what you will see in college algebra, because really college algebra is the study of functions, and the functions we're going to talk about the most are the ones in this lesson. So it really is the prep work for making sure you know what all the different shapes we're going to be working with are. All right, so first, what are parent functions? There are several basic functions that we encounter and work with in mathematics that can be referred to as toolkit or parent functions. Okay, we're going to be using the word parent function the most, but toolkit is also used quite often. You know, the old saying, like if you have a utility belt like Batman and you're going to throw out your different tools, well, the tools we work with in mathematics tend to be functions because functions do the work. All right, so what are we going to see other than parent functions then in this class? Because there's only about 9 of them in this lesson. So is that really all we see? And the answer is no. We see tons and tons and tons of functions out there, but most other functions we see, not all, but most, are transformations of the ones we're about to see. Where a transformation can either be rigid or non-rigid, meaning it can either change the shape of the graph or it can just move it side to side or up or down. So first we're going to go through each of the parent functions and some key aspects to each of them. And then after that, we're going to talk about how to transform those functions. So first, let's learn about all the parent functions, starting with our most simple one, which is just y equals x. Y equals x is the most basic function. It makes a straight line. This is called a linear function because it has an exponent of 1. Therefore, it makes a straight line. And if we want to plug in all these x values you see in the table, well, nothing's going to happen to them because the equation is just y equals x. So we're not going to do anything to them. So if you plug in -2, you output -2. Plug in -1, you output -1. 0 goes to 0, 1 goes to 1, 2 goes to 2. Nothing's really changing there. And if we were to graph each of these, we can throw on the points 0, 0, 1, 1, 2, 2, -1, -1, -2, -2. And all that's happening is we're making a straight line that goes up and to the right. So that is our most basic function. It has a constant slope and is just going up and to the right. That is a linear function. If we increase the exponent by 1, so instead of dealing with x to the power 1, we have x squared. This is now called a quadratic function, and it is probably considered the most important function in mathematics. It's something we see just everywhere all the time. So we see linear functions a lot too. I don't want to discount those, but quadratics probably right up there as the most important. And all we're going to do is take the input and multiply it by itself or square it. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. Notice that the negative signs disappeared when we squared them because a negative times a negative is positive. And so what happens when we graph this is the right side of the graph goes up. So you can see 0, 0, 1, 1, and then 2, 4 would be up here. But the left side of the graph, instead of going down the way a linear function did, it's also going to go up. -1, positive 1, -2, positive 4. And on both sides, we're going to create this upward curve that looks like a U shape. This is, again, probably the most important function. It's the thing we work with the most in college mathematics, and you're going to see it all the time. But what gives students the most trouble is quite honestly just the name. It's a quadratic function. So x squared, quadratic, and again, notice both sides go up. Notice that so far we have infinite domains, meaning nothing is restricted, and we also don't have any breaks or jumps in the graph. Nice, continuous, smooth graphs. That's going to continue for our third function, x cubed. Okay, this is called a cubic function. And all we do is take the input and multiply by itself 3 times. So -2 cubed is -8, -1 cubed is -1, 0 goes to 0, 1 goes to 1, and +2 goes to +8. When we graph this one, notice the negative sign stayed attached. And so on the right side of the graph, it goes up much like it was doing before, although it goes up faster than it did before. But on the left side of the graph, instead of curving up like a U shape, it's going to go down. And so the right side goes up, the left side goes down, and we end up with this, what I call a squiggly shape, where it's not going up in a straight line, but it's close, right? You can see a lot of similarities between x to the power 1 and x to the power 3. They both go up and to the right, they both go down and to the left, but the difference is that the cubic function is curved in the middle and it's growing much, much faster than the linear function is. So that's why it appears to be going almost straight up on the right side. All right, our next one is 2 to the power x. This is a specific exponential function because it's a 2, but we could have more generally just b to the power x, where b could be any number, any positive number, I should say, other than 1. But I chose 2 to the x because it's the easiest exponential function. And that is the name of it, exponential function. And all we're going to do is take the input and make it the exponent on the 2. So 2 to the power negative 2, I'm going to write this one out real quick. 2 to the power negative 2 is 1 over 2 to the positive 2, which is 1/4. So 2 to the negative 2 is 1/4. When we plug in negative 1 as the exponent, we're going to get 1/2. 0, 2 to the power 0 is just 1. 2 to the power 1 is 2, and 2 to the power 2 is 4. This is a pretty interesting shape because instead of going down on one side or up on both sides, or really just going up or down in general, we're going to have it flatten out on one side. So these numbers over here, 1/2 and 1/4, cause the left side of the graph to just get smaller and smaller and smaller as they approach 0. So what this graph actually does is on the right side, it goes up real fast. So 1, 2, 2, 4. And then if we went and plugged in 3, it would be all the way up at 8. And it would just keep growing faster and faster and faster on that side. So this basically points up to infinity. But on the left side, instead of going down to negative infinity, it actually flattens out to 0. And so what happens with this graph, we go ahead and draw a dotted line across, is we have what's called a horizontal asymptote at y equals 0, which means it never actually gets to y equals 0. It gets infinitely close, but it never actually reaches it. And that is the most key characteristic of an exponential function, is that it flattens out on one side. Notice so far all of our domains have been all real numbers, negative infinity to infinity. There's no breaks in the graph, but we did finally just have a weird one where the left side flattens out instead of going down to negative infinity. All right, now we're going to end the streak of infinite domains because the next one is the square root of x, called a square root function. All right, also sometimes just called a radical function, but specifically this is a square root function because the index is 2. And the square root function is only defined if x is greater than or equal to 0. So notice the numbers in the table changed. Instead of negative 2 to positive 2, we're now starting with 0 and we're going up in the positive direction. And notice that all the x values we're going to plug in are perfect squares. You can plug in non-perfect squares to a square root function, but you're going to get ugly decimal answers out, and we would prefer to have our numbers be nice and clean to make them easy to graph. So all we're going to do is square root each number. Square root of 0 is just 0, 1 is 1, square root of 4 is 2, square root of 9 is 3, and square root of 16 is 4. So we can see that this graph goes up and to the right, but it doesn't go up particularly quickly. It actually goes up very slowly, and it doesn't technically flatten out. Okay, it continuously goes up. It never reaches a maximum, but it goes up very slowly over time. So like next number we'd have to plug in for a perfect square would be 25, and then 36, and then 49, and then 64. And notice those numbers are getting farther and farther apart. So to go up 1 on the y-axis, it gets harder and harder. You got to plug in really big numbers eventually. The other key characteristic here that we need to make sure we note, though, is that the domain is no longer all real numbers. The domain is now only x greater than or equal to 0. Okay, so we cannot plug in whatever we want. If we plug in anything negative, we're going to get imaginary outputs, which we cannot graph. Okay, so a restricted domain for this one. Number, or not numbered, but the next one, we now have the cube root of x. Okay, so instead of square root, this is now a cube root function. But confusingly, this is also just called a radical function because it has a radical in it. But you can see now why we don't use that as the name usually. It's because then they both would just be radical functions. So to be more specific, we have a square root and we have a cube root. All this does is check what to the power 3 equals that x value. So if we have an x value of -8, that means -2 was the y value. -1 would be -1, 0, 0, 1, 1, and 8, +2. And what this is going to do on the right side is look almost the same as the square root function. 0, 0, 1, 1, and 8, 2. It's not quite the same, but it's a fairly similar shape where it's going up but kind of flattening out. But on the left side, it actually exists and it just mirrors the right side. So instead of non-existing, it does exist. And what you should notice it looks like is almost exactly the same as the cubic function, just turned sideways. Okay, so very, very close relationship between a cubic function and a cube root function, as you should probably expect. And there's also a very clear relationship between a quadratic, the graph of x squared, and a square root function. Notice that the shape we drew here is half of a sideways parabola. So if I continued this, it would look like a U shape, just like this graph up here for the quadratic looks like a U shape. Okay, they are both parabolically shaped. A parabola is what we call this U shape up here. The only difference is that for the square root, when we turn it sideways, we do not have the lower half because then this would not be a function. Because remember, it has to pass the vertical line test. So if we had both sides of that sideways parabola, it would no longer be a function. All right, moving on, we got a couple more. We have 1 over x right here. 1 over x has a couple names. Some people call it the reciprocal function, but generally speaking, we will refer to this as a rational function, where rational just means that we have a variable in the denominator. So we have a fraction specifically with the variable in that denominator. And what we're going to see real quick here is that 0 is not an acceptable input because 0 would make the denominator 0, which is strictly not allowed. So when we plug in -2, we get -1/2. Plug in -1, we get -1. But if you try to plug in 0, we're going to get an undefined value because 1 over 0 does not exist. We don't know what that is. When you plug in 1, though, you just get 1, and plug in 2, you get +1/2. Now, this table does not actually do a great job of showing us what's happening here because if I label just these 4 points, 1, 1, 2, 1/2, and -1, -1, -2, -1/2, those dots don't really show us much, do they? You really can't tell what's happening. And so I happen to know, because I'm familiar with these functions, that this graph, let me zoom out a little more, that this graph is going to have 2 branches, one that goes on the left side and one that goes on the right side. But in order to get that shape, you need a graph a lot more than just 4 points. So we could use a graphing calculator and see exactly what it looks like. So in here, if I type in 1 over x, you can see the shape there matches what I just drew. But you really need quite a few points in order to uncover that shape. So now there's a few key characteristics here. Number 1 is that x cannot be 0. So x is not allowed to be 0. Most important thing, you cannot divide by 0 here. Just like with the square root, x had to be non-negative. But the other thing here is that we have a vertical asymptote going down the middle here, which is a border where nothing touches at x equals 0. So we have a vertical asymptote at x equals 0, and horizontally, we have a horizontal asymptote at y equals 0, which if you recall, we also had on the exponential function. So this graph, despite me drawing it looking kind of messy, this graph never touches these two asymptotes, horizontal or vertical. So there are pieces of the graph that are just not allowed to be touched. Along with that, just a little bit of vocabulary. We call each of these sides branches. So the left is a branch and the right is also a branch. Whenever you have a graph that is cut up into pieces, we call those pieces branches of the graph. All right, next one is y equals the absolute value of x. So those two vertical lines tell us to take the input and just make it positive. So this is called an absolute value function. And all it does is take negatives and make them positive, and it leaves positives alone. So -2 becomes +2, -1 becomes +1, 0 stays the same, and 1 and 2 stay the same. So it just takes the negatives, flips them up to be positive. So if we graph these, what it looks like is a straight line on each side, where on the right side, the line is going up and to the right, and on the left side, the line is going down and to the right. And so it creates a V shape, where notice that both those lines are straight. They're not curved like a parabola. So it creates a hard corner right here. All right, so absolute value makes a V shape. And if we want to be real technical, that spot in there where that V shape goes is called a cusp. So instead of a vertex, which is what we have on a parabola, we call it a cusp, where it is two straight lines coming together. So it's not super smooth. All right, so now those are all the parent functions. Now we need to talk about transformations. And there's quite a few rules that go along with this to help you guys understand and be able to play around with all these things we're about to go over. If you scan that QR code, what it's going to take you to is this Desmos page. And you can make a copy of this Desmos page if you wish, or you can just use it as is and rescan the QR code every time. But what you can do is change this f of x function to be whatever you want. So right now I have it as x squared. You could make it x cubed, absolute value of x, whatever you want. But that is the red graph being shown. So if you wanted to change it to, let's say, x cubed, you can just go ahead and switch it out. Make it x cubed, x to the fifth, whatever tickles your fancy. But I'm going to leave it as x squared. And then all the transformations we're going to talk about happen down below here. So if you want to adjust any of these, all you have to do is move the slider around and the graph will change. So we're going to go through what each of these do, but after we've done that, if you want to play around with them, if you just slide these from side to side, see the blue graph now looks different than the red graph. And you can go all the way in both directions so you can see it flipped upside down. Okay, so you can see that if you move the H, it'll move it to the left or to the right. And if you move the K, it'll move it up or down. And the S stretches it horizontally. So it bends up and down that way. All right, so you can play with that to better familiarize yourself with everything we're about to go over as we go through. All of these examples are going to be done using x squared over here on the side. So I'm going to tell you what each thing does, and then on the right, it's an example using x squared, which is the same graph that that QR code takes you to. But again, you can change the function after you scan the QR code if you wish. All right, so few of these to go through. First one, we have f of x plus k. So f of x is our function, and what we're doing is we're adding k to the function. So the question is, what does that plus k do? Well, because it's outside of the function and it's a plus, that plus is going to be a vertical shift up by k units. So for example, over there on the right side, if I take g of x and I add 2, that is going to move the graph up 2 units. And if g of x is x squared, then this looks like x squared plus 2. So notice g of x right here stayed as x squared. We did not change what g of x is, it's just x squared. But then this plus 2 is on the outside of the function. And that takes the graph and shifts it up 2. So if you wanted to see that after you scan the QR code, all you have to do is take the k, which is down at the bottom, and move it up or down. So if I set k to be 2, it's 2 higher, could go 4 higher, 5 higher, however much higher or lower you want. All right, notice if I make k negative, it goes down. Okay, so that's going to be our next bullet point. Over here, f of x minus k now. So if we subtract k, all that's going to do is vertically shift our graph down by k units. And so on the right side, you can see x squared minus 3. This is going to be down 3, whereas the first one was up 2. Okay, so that's if we want to go up or down, we put k on the outside of the function. If we want to move left or right, we put h for horizontal shift on the inside of the function. So right here, this plus h on the inside, f of x plus h, where it's in the parentheses, is a horizontal shift left by h units. So for example, if we have g of x plus 4, that's the same thing, if g is x squared, as x plus 4, the whole thing squared. This is going to move the graph left 4. Okay? If instead it's x minus h, this is going to be a horizontal shift right by h units. So x minus 5, the whole thing squared, was shifted right by 5. Okay, so notice that horizontal kind of works the opposite of what you would expect. When we did a vertical shift up, up meant plus k. But when we're doing a horizontal shift, plus h actually means left, which is the negative direction. So for horizontal shifts, it works opposite of what you would normally expect. All right, next one. We have negative f of x. This negative sign in front causes a reflection, and because it's outside of the parentheses, it's a vertical reflection over the x-axis. So we flip vertically to, instead of facing up, we face down. So on the right side, negative g of x is negative x squared. That is a vertical reflection. If instead of just a negative sign in front, we put this letter a, which could be any number, that is going to be a vertical dilation. Okay, where dilation means to stretch or compress the shape. So if a is greater than 1, that's going to be a vertical stretch. It's going to make our graph taller and narrower. Okay, it's going to stretch the graph towards the ceiling and towards the floor. And if a is between 0 and 1, it's going to be a vertical compression. So let's go ahead and go back to see what this looks like over here. Let me just reset this. Did I go too far? There we go. Make this back to x squared real quick. Okay, so I have my parabola. Right now, a is 1. Notice that you can't see both graphs. Okay, you can only see one graph over there. If I change a to be 2, see how now it's thinner than it was before? I moved a all the way to be 4, and see if I keep making it bigger, it keeps getting thinner and thinner. So what's happening is it's stretching the graph up. Imagine if the graph was made of Play-Doh and you pulled it towards the ceiling, it would get thinner and thinner as you pull it. And what it's actually doing is it's multiplying all the y values, or the outputs of the function, by this a value. So by multiplying by a number bigger than 1, it makes them go higher up. Okay, it stretches them from the x-axis. If I move a the other direction to be less than 1, see how now the blue graph is really wide? Okay, so if you can imagine pushing the graph down, it makes it compressed or wider. All right, so we can either stretch or we can compress our graph. So on the right side over here, where it says 2x squared, that is going to be a vertical stretch. Okay, vertical stretch. Or you could say that it's a dilation by a factor of 2. Now, everything we just did for vertical also works for horizontal. So we could say that f of negative x right here is a horizontal reflection over the y-axis. So instead of flipping up and down, you flip left and right. And instead of a negative sign there, we could put an actual number that we call s, which will be a horizontal dilation. And just like before, it's either going to stretch or compress the graph. But now instead of pulling it up and down, you would squish it or pull it left and right. Unfortunately, it works the opposite of how vertical works, which makes it slightly harder to remember. If s is bigger than 1, it is going to be a horizontal compression. And if s is between 0 and 1, it's going to be a horizontal stretch. So it's the exact opposite of what vertical was. Don't let that stress you out though. Horizontal dilations are something we almost never use. So the important ones to remember are the reflections, the shifts, and the vertical dilations. But quite honestly, these ones down here, okay, this last box is rarely used. So you don't need to stress over it too much. It will show up again when you get to pre-calculus if you take that class. But until then, it's not going to really be mentioned much. All right, so over on the right side, we have g of 2x is equal to 2x, the whole thing squared, where because this number is on the inside, that means it's a horizontal dilation. So we could say it's a horizontal dilation by a factor of, and then we could say 2 or 1/2, depending on which direction it's going. And in this case, if we follow the rules, because 2 is bigger than 1, this is going to be a horizontal compression. All right, so horizontal compression. But again, don't worry too much about the horizontal dilations. They're not going to be heavily used in college algebra, much more of a pre-calculus topic. All right, now we're just going to do some examples. So number 1, we want to describe the transformations from f of x equals x to g of x equals x plus 1. If you use the QR code I gave you, you can actually see this visually. So if I come back over here and reset this to be at 1, if I change my function, instead of x squared, if I just make it x, okay, then I have a straight line. And what our graph just told us to do is instead of looking at plain old x, we want to look at x plus 1. So if I change the k value down here to be 1, notice the difference between the blue line and the red line. The blue line is 1 block higher than the red line. So by changing from x to x plus 1, so by making k equal 1, I moved the graph up 1 unit. So over here for number 1, all I have to do is say shift up 1. Okay, we went 1 unit up. And if we wanted to, we could label that 1 as the k value, but we don't need to. All right, number 2, we have x squared becoming x squared minus 4. So in nearly the same way as the previous one, instead of a plus 1, now we have a minus 4. That is going to be a shift down by 4. Okay, that minus 4 on the outside just moves us down 4. Number 3, up in the top right, we're going from absolute value of x to absolute value of x minus 2 with a plus 3 on the outside. Okay, so we have two things happening here. The minus 2 on the inside is the h value. That's going to be a shift, but because it's minus 2, it's going to be right by 2. And then the plus 3 on the outside, just like number 1, is just going to shift us up by 3 because positive 3. So remember that for horizontal, if it's minus a number, you go right by that number. And for vertical, if it's plus, you go up. Okay, the next one's going to show us the opposite direction for horizontal shifts. We have square root of x going to 4 square root of x plus 1. So the plus 1 on the inside is going to be a shift left 1, okay, because it's plus 1 on the inside of the square root, so that's left 1. And the 4 in front is going to be a vertical dilation by 4, or by a factor of 4. That means that we are going to be stretching our graph by a factor of 4. Moving on to number 5, we're going from f of x to 3 f of x plus 1. So we have two transformations happening here, the 3 in front and the 1 in the back. The 3 in front is going to be a vertical dilation by 3. And the 1 in the back is going to be a shift up 1. Okay? And if you want to know about the order, it actually does very much matter what order we do things in. So whenever we're talking about a combination of shifts and dilations, you want to make sure that the shifts go after the dilations when they involve the same direction. Okay, so dilate before you shift. But that only has to be true if they're both vertical or both horizontal things. So you dilate before you shift in this case because it's a vertical dilation and it's a vertical shift up. So the dilation comes first. In number 4, I shifted before I dilated because it was a horizontal shift and a vertical dilation. So because one was horizontal and the other was vertical, it doesn't actually matter which one you do first. But when both are vertical, so vertical at dilation and shift up, then you need a shift after you dilate. So the dilation comes first. Okay, number 7. Number 7, we're going from f of x to f of negative x minus 5. There's a small issue with how this is written though, because it doesn't match our format from before, where we needed to have x plus or minus h on the inside. So what we have to do is rewrite this in here as f of a negative sign and then x plus 5 in parentheses. So notice I pulled the negative sign out of those two terms there. We always need to have it in this format in order to properly read off that this negative sign is a horizontal reflection and that the 5 is actually positive. Okay, so it's a horizontal reflection, and then this plus 5 is a shift left 5. Okay, so you have the reflection and then you have the shift. Most students, though, would mistakenly say that this is a shift right by 5 because in the original problem, it looks like minus 5 right here. Because we need to pull out the negative sign here to have x all by itself, okay, x needs to have a coefficient of positive 1 right here. That actually makes it a plus 5, so it's a shift left 5. All right, number 6, we're going from f of x to negative 1/3 f of x minus 4. So a lot's happening here. We have this negative sign in front, which is a vertical reflection. Then we have the 1/3 right here. Okay, the 1/3 is a vertical dilation. And then we have the minus 4 in the back, and the minus 4 is a shift down 4. So we're going to reflect, we're going to dilate, and then we're going to shift. A lot of vertical movement happening there. So this graph is going to face down, and then it's going to get more compressed vertically, and then it's going to shift down some more. All right, so you go ahead, pause the video, try that last one there real quick if you haven't taken any time to try these yet. All right, and for that you try one, we're going from f of x to negative 4 f of x plus 2, where the negative sign in front is going to be a vertical reflection, just like the previous one. Then the 4 next to it is going to be a vertical dilation by 4. And then in the back, we have a plus 2, but the plus 2 is inside of the parentheses. It's attached to that x inside the parentheses. And so it's a horizontal shift. And whenever it's horizontal, remember, it works opposite of what you might think. And so plus 2 is a shift left by 2. All right, so now that we've gone that direction with these, we have just a couple where we're going to write the notation instead. So we had the notation in those past couple. Now we're going to create the notation. Number 8 says the function f of x was shifted left 5 and down 2 and was vertically stretched by a factor of 3. We want to write the equation for the transformed function. So we're going to call our transformed function g of x, okay? Because the original one is f of x, so our new one's going to be g of x. And g of x is going to be a transformation of f of x, where we've done these 3 transformations to it. So a vertical stretch by a factor of 3 means we're putting a 3 in front of the function. And then we have f of, and since it's a shift left 5, it's going to be x plus 5 inside is how you move it to the left. And then down 2 means on the outside of this, we're going to have minus 2. Okay, so we have the dilation, we have the left, and we have the down. All right, one more for you guys to try. So pause the video, give it a chance. All right, that last one says the function f of x was shifted right 1 and was reflected over the x-axis, which is a vertical reflection. So we're going to say that the transformed function, g of x, is equal to, we're going to go to the right by 1, and we're going to go reflect over the x-axis. So to reflect, we have to put a negative sign in front of the function, and then it's f of x. And because we're going to the right by 1, that means inside of the parentheses, we're going to put a minus 1. And that minus 1 moves it to the right by 1. All right, and that is all I have for you on parent functions and their transformations. I know it was a lot in this one, but a lot of good information that's going to be useful moving forward. Hope you enjoyed it, and I will see you on the next one.